Black holes are not the cosmic vacuum cleaners you think they are. That simple image is just a shadow cast by a far stranger reality. We are about to go on a journey to the very edge of known physics, exploring 30 of the most incredible unknowns about these objects. You will walk away with a completely new understanding of what a black hole might truly be. We will confront puzzles where information vanishes forever and where time itself loops back on its own tail. We will question if our entire universe could be hiding inside one. This is not a list of simple facts. It is a deep dive into the mysteries that keep physicists awake at night. Are you ready to have everything you know about space and time turned inside out? Our first great unknown strikes at the very heart of reality. It is called the information paradox, and it is a war between the two greatest theories of physics. On one side stands quantum mechanics, the rule book for the very small. Its most sacred law is that information can never be destroyed. If you burn a book, the ash and smoke still contain, in principle, the exact arrangement of atoms that spelled out every word. The information is scrambled, but it is not gone. On the other side stands Einstein's general relativity, which describes gravity and the fabric of space-time. It paints a very different picture. When something falls into a black hole, it passes the point of no return, the event horizon, and is crushed into the singularity at the center. According to relativity, that object and every single bit of information about it is erased from our universe forever. It is as if the book is not just burned, but the very concept of the book is deleted from existence. For decades, physicists accepted this grim erasure as the price of a black hole. Then Stephen Hawking changed everything. He showed that black holes are not completely black. Due to weird quantum effects right at the event horizon, they slowly leak a faint glow of particles, now called Hawking radiation. This radiation carries away energy, causing the black hole to shrink and eventually evaporate completely. And here lies the paradox. Hawking's calculations suggested this escaping radiation was completely random, like thermal noise. It carried no information about what fell in. So, when the black hole vanishes, all the information about every star, planet, or book that ever fell into it vanishes with it. Quantum mechanics screams that this is impossible. General relativity shrugs. This is the paradox, a fundamental contradiction that means one of our core theories is wrong, or at least incomplete. Desperate solutions have been proposed. One of the most radical is the firewall hypothesis. It suggests that instead of a smooth entry through the event horizon, there is a searing wall of high-energy particles that incinerates anything trying to cross. This firewall would preserve information by not letting it enter in the first place, but it violates relativity's principle that falling into a black hole should be uneventful until you're torn apart by tides. So we are left with a haunting question. Is information truly lost in a cosmic shredder, or is it somehow preserved in a way we cannot yet see? The fate of reality's memory depends on the answer. That paradox of lost information points us toward the black hole's deepest secret, the very source of all this cosmic confusion. This brings us to our second great unknown, the ultimate destination for everything that falls in, the singularity itself. We describe it as a point of infinite density, a place where all the mass of a collapsed star is crushed into a volume of zero size. But infinity is not a physical answer. It is a mathematical scream, a sign that our equations have broken down completely. General relativity gives us a beautiful map of space-time, but at the singularity, that map tears. It is the edge of the map marked with the warning, "Here be dragons." We simply have no physics to describe a place where density becomes infinite, where gravity becomes infinite, where the very concepts of space and time cease to have any meaning. It is the ultimate dead end for our understanding. So, physicists are forced to ask a radical question. Is the singularity truly real, or is it just a placeholder for something we do not yet comprehend? The leading idea is that the monstrous gravity of a black hole must awaken the strange rules of the quantum world, a theory of quantum gravity we have yet to fully discover. This new physics would not allow for an infinitely small point. Instead, it might replace the terrifying singularity with something entirely new. One fascinating proposal from string theory is the fuzzball. Imagine the black hole's core not as a pinprick, but as a tangled, vibrating ball of cosmic strings, the fundamental threads of reality. This fuzzball has a surface and a finite size, and it contains all the information about what fell into the black hole, neatly stored within its complex structure. There is no singularity, no point of infinite anything, just a bizarre, fuzzy object that respects the laws of quantum mechanics. Another idea from loop quantum gravity suggests something called a Planck star. In this view, the collapse does not go on forever. When matter is compressed to an incredibly small scale, a new, repulsive quantum force kicks in like a cosmic spring. The collapse halts and the core rebounds, but it is trapped inside the event horizon. From the outside, we would still see a black hole, but inside, at the very center, there could be a tiny, ultra-dense remnant of the original star, frozen in a state of eternal bounce. These are not just wild guesses, they are desperate, creative attempts to answer the most basic question: what is actually there in the dark heart of the darkness? Is it a mathematical phantom or a physical object stranger than any fiction? Until we have a theory that marries gravity and the quantum world, the singularity remains the greatest blank space on our map of reality. The event horizon is only the beginning of the nightmare. Crossing that invisible threshold does not mean you are instantly annihilated. According to Einstein's equations, you would still have some time, perhaps minutes or hours depending on the black hole's size, before the final curtain falls. Your fate is dictated by the black hole's interior geometry, a landscape warped beyond all recognition. The force of gravity at your feet, already closer to the center, becomes unimaginably stronger than the force at your head. This difference, the tidal force, stretches you into a long, thin strand of atoms, a process vividly called spaghettification, but that is just the gruesome prelude. The real mystery is what happens next to the very substance of your being. Where does that stream of particles ultimately go? The classical answer is a grim, one-way journey to the singularity. You and every bit of your information are pulled inexorably toward that central point of infinite density where you are crushed out of existence. Yet, as we just explored, the singularity is likely not the final answer. So perhaps your matter does not simply vanish into a mathematical error. Some theories suggest that as you fall, you do not encounter a point but a surface. In the fuzzball model, your stretched particles would merge with the vibrating, stringy structure of the black hole's core. You would not be destroyed but transformed, your information encoded into the intricate quantum vibrations of the fuzzball itself, becoming a permanent part of the black hole's internal architecture. Another possibility is even stranger. The interior of a black hole, according to the equations, is not static. Space itself is falling inward faster than the speed of light toward the center. Some physicists interpret this to mean that inside the event horizon, the roles of space and time literally swap. What was the radial direction, moving toward the center, becomes a time-like direction, meaning you cannot stop moving forward any more than you can stop time in the outside universe. The singularity is not a place you reach in space, but a moment you hit in time, a final, unavoidable future for everything inside. The geometry within could be a chaotic, ever-changing whirlpool of space-time, where matter is not just crushed, but utterly scrambled and reconfigured by forces we cannot yet name. So, does matter get crushed, or does it become a new layer on a cosmic onion, or data written on a quantum hard drive? We simply do not know what the interior of a black hole looks like or what truly awaits there. It is a realm forever hidden by the ultimate curtain, where our physics becomes a collection of question marks. If the interior of a black hole is a one-way street to oblivion, could there be a cosmic exit door? Einstein's own equations hint at a bizarre possibility, a theoretical mirror image of a black hole known as a white hole. While a black hole's event horizon is a boundary from which nothing can escape, a white hole's horizon is a boundary that nothing can cross from the outside. It is a region of space-time that only emits matter and energy, erupting light and particles in a perpetual cosmic fountain, forever refusing to let anything in. Mathematically, it is a perfectly valid solution, the other side of the black hole coin. But if black holes are formed from collapsing stars, what natural process could possibly birth a white hole, an object that defies the very flow of entropy and time as we experience it? One thrilling, though highly speculative, idea is that a white hole is not a separate object at all, but the other end of a black hole. Imagine a tunnel, a wormhole, connecting the crushing singularity of a black hole to the erupting fountain of a white hole in some distant part of the universe, or even in another universe entirely. In this view, the matter that falls into a black hole might not be destroyed but violently expelled from a white hole elsewhere. It is the ultimate cosmic shortcut and recycling system. An even more profound possibility ties white holes to the very beginning of everything. Some cosmologists have suggested that the Big Bang itself could have been a primordial white hole event, a single point of space-time erupting with all the energy and matter of our universe. Instead of a mysterious singularity from nothing, our entire cosmos could have been born from the white hole end of a black hole in a parent universe. This creates a breathtaking, almost cyclical picture of reality where universes are born from the deaths of others. Yet, for all their mathematical elegance, white holes face a serious problem. They appear to violate the second law of thermodynamics, which dictates that disorder in the universe always increases. A white hole spewing out ordered energy seems to reverse this flow. Most physicists believe this makes them physically impossible in our universe, or at least incredibly unstable, collapsing instantly into something else the moment they try to form. So white holes remain in the realm of tantalizing what if. They are the brilliant, rebellious twins of black holes, written into the fabric of Einstein's universe but perhaps forbidden from ever stepping onto the cosmic stage. Their existence would rewrite the story of creation and connection, offering a universe far stranger and more interconnected than we ever dreamed. For now, they are brilliant ghosts in the equations, waiting for a discovery that would shake the foundations of physics. The horizon's perfect circle is a comforting lie. In every artist's depiction and textbook diagram, we see that smooth, dark sphere, a flawless boundary between the known and the unknowable. But reality is far messier and more dynamic. An event horizon is not a rigid wall. It is a living surface, a membrane of pure geometry that breathes, stretches, and contorts in response to the black hole's violent life. Its true shape is a complex dance dictated by three factors: mass, spin, and electric charge. A simple, non-spinning black hole with no charge, described by the Schwarzschild solution, does have that perfect spherical horizon. But these are likely rare in our universe. Most black holes are born from spinning stars, and that rotation carries over, accelerating to incredible speeds as the core collapses. This creates a Kerr black hole, and its horizon is profoundly different. The centrifugal force of the spin flattens the black hole at its poles and bulges it at the equator like a cosmic spinning top. But the strangeness does not stop at the horizon's edge. Surrounding a rotating black hole is a region of twisted space-time called the ergosphere, a squashed bubble where something unbelievable happens. The black hole's spin drags the very fabric of space-time around with it, like a spoon stirring a pot of thick honey. Within the ergosphere, this drag is so powerful that nothing, not even light, can remain stationary. Everything is forced to move in the direction of the spin. This is not the event horizon. You could still escape from here, but you will be swept along in a cosmic current you cannot fight. Matter and energy whirling through the ergosphere can be slingshotted outward with even more energy than they came in with, a theoretical process called the Penrose mechanism. Now imagine a black hole actively feeding, pulling a stream of gas from a companion star. That incoming matter carries its own angular momentum, striking the horizon like a fire hose hitting a spinning sphere. The impact creates hotspots, ripples, and distortions. The horizon itself wobbles and pulsates, absorbing this new energy and angular momentum, its shape constantly evolving in real time. It is a shape born from chaos, a fingerprint of the black hole's entire violent history. So, the next time you picture a black hole, do not see a static hole in space. See a lopsided, wobbling whirlpool of pure gravity, its form a silent testament to the furious spin and the last screams of matter it has consumed. This dynamic reality changes how we might one day observe them, not as simple shadows, but as shimmering, vibrating objects in the cosmos. The smooth horizon we just pictured might be hiding a secret texture. For decades, physicists have operated under a powerful principle called the no-hair theorem. It states that a black hole, in the end, is the simplest object in the universe. No matter how complex the star that formed it, no matter what you throw into it, all its distinguishing features are erased. It retains only three pieces of information that we can detect from the outside: its mass, its spin, and its electric charge. That is it. A black hole made from a collapsed star and one made from 1,000 refrigerators would be utterly identical if their mass, spin, and charge matched. They are cosmic bald heads with no hair, no unique features to tell their history. This elegant idea is what makes the information paradox so devastating. If a black hole only has three numbers, then everything else, every proton, every memory, every bit of data about what fell in, is truly gone forever. But what if the theorem is not the final word? A new and exciting idea called the quantum hair conjecture suggests black holes might not be bald after all. They could possess a faint, subtle fuzz of information, imprinted not in their classical shape, but in the quantum fields that surround them. Think of it this way. The classical view sees the event horizon as a smooth geometric boundary, but in the quantum world, empty space is not empty. It is a seething, bubbling foam of virtual particles popping in and out of existence. These quantum fields fill the universe, and they must also interact with the immense gravity of a black hole. The conjecture proposes that when matter falls in, it leaves a tiny, permanent imprint on these surrounding fields, like a stone creating ripples that never fully settle. These imprints would be incredibly subtle, a kind of quantum memory etched into the very fabric of space-time around the horizon. This hair would not be something you could see with a telescope. It would be a pattern in the underlying quantum information, a fingerprint of everything the black hole consumed. If this is true, it offers a breathtaking solution. The information is not lost inside the singularity. It is preserved on the outside, woven into the quantum fuzz clinging to the horizon, waiting to be decoded by a physics we do not yet fully possess. It bridges the war between quantum mechanics and gravity, suggesting a black hole is not a destroyer of information, but its most meticulous and bizarre archivist. The universe, it seems, might keep a receipt for everything, even after it vanishes into the dark. That quantum hair, if real, is a whisper from a black hole's past. But some black holes have a past that defies all logic, a history written in the very first pages of the universe. Scattered across the cosmos at the hearts of nearly every galaxy, we find true monsters, supermassive black holes. These are not the remnants of dead stars. They are cosmic sovereigns, weighing millions or even billions of times the mass of our Sun, and their existence poses a colossal puzzle. We have found quasars, the blazing beacons of matter, falling into such supermassive black holes. shining from when the universe was less than 1 billion years old. How did these titans grow so unimaginably large, so terrifyingly fast? A star-sized black hole simply could not eat enough, fast enough, to reach such sizes in the cosmic blink of an eye after the Big Bang. So how did they get there? The leading theory involves a cosmic shortcut, a scenario called direct collapse. In the early, dense universe before the first stars ignited, there could have been vast clouds of pure hydrogen and helium gas. Under the right conditions, these clouds might have skipped the star-forming stage entirely. Instead of fragmenting into many stars, an entire giant cloud, hundreds of thousands of times the mass of the Sun, could have collapsed directly under its own weight. With no nuclear fusion to push back against gravity, it would have fallen straight into a massive black hole seed, a behemoth born in a single, catastrophic event. This seed, already tens of thousands of solar masses, would have had a tremendous head start, a huge appetite ready to devour the gas-rich young universe and grow into the supermassive giants we see. Another possibility reaches back even further into the strange physics of the universe's first moments. These are primordial black holes. They would not have formed from stars at all, but from the intense density fluctuations in the hot, expanding soup of the infant cosmos. A region just slightly denser than its surroundings could have collapsed directly as space itself stretched. These primordial black holes could be any size, from microscopic to massive. If some were born with the mass of 1,000 suns or more, they would have been perfect seeds already in place and waiting to grow when the first galaxies began to form. They are cosmic fossils from the first second of time. Yet another idea suggests a frenzied, chaotic nursery. In the crowded core of a young star cluster, many early stellar black holes could have merged together over and over, a violent game of gravitational pinball, rapidly building up a heavy seed. Then, this merged object would have sunk to the center of the emerging galaxy, where a vast reservoir of gas awaited, fueling a growth spurt of epic proportions. Each theory paints a different picture of cosmic dawn, one of silent, direct collapse, of random quantum births, or of violent stellar mergers. The truth is, we are still looking for that first giant seed. Finding it would tell us not just how black holes grow, but how galaxies themselves were born around these dark, gravitational anchors. The origin of these supermassive beasts is the origin story of cosmic structure itself. Those ancient seeds might still be with us, hiding in plain sight. Our eighth unknown asks a staggering question. Could black holes, specifically those primordial ones from the beginning of time, be the very substance of dark matter? For decades, we have known that most of the matter in the universe is invisible, a mysterious dark matter that holds galaxies together with its gravity. We have hunted for exotic new particles with no success. So, perhaps the answer is not a particle at all, but an astronomical object we already know exists. Primordial black holes formed in the first chaotic second of the Big Bang could be the perfect candidate. They are dark, they have mass, and they would cluster around galaxies just like the dark matter we observe. It is an elegant, almost simple idea. The entire cosmic dark matter halo of our Milky Way could be a vast, diffuse cloud of countless ancient black holes. But if they are everywhere, why have we not seen them? The answer lies in their size. Observations have ruthlessly ruled out vast swaths of the possible mass range. If dark matter were made of black holes as massive as stars, we would see their gravitational effects distorting the light of distant stars far too often. We do not. If it were made of trillions of tiny black holes, each no heavier than an asteroid, they would have evaporated by now due to Hawking radiation. The window that remains open is intriguing. Primordial black holes with masses similar to a large planet or even a small star are still possible. Think of an object with the mass of Earth but crushed into the size of a grape. Or one with the mass of a mountain compressed to the width of a proton. These would be elusive but not invisible, Our main method for hunting them is called gravitational microlensing. If such a black hole drifts between us and a distant star, its gravity will act as a tiny lens, bending and magnifying the star's light for a brief period, causing it to brighten and then fade in a specific pattern. Massive surveys like the optical gravitational lensing experiment scan millions of stars looking for these telltale flashes. They have found some mysterious lensing events, but not nearly enough to account for all the dark matter. So, while primordial black holes could make up a fraction of the dark universe, they are unlikely to be the whole story. They remain brilliant ghosts, possible inhabitants of the dark, but perhaps not its sole architects. The hunt continues, scanning the darkness for shadows born in the first light of creation. Rotation does not just warp the horizon, it shreds the rulebook for the black hole's interior. Step inside a spinning Kerr black hole, and you leave the familiar universe behind. The first thing you would encounter after the outer event horizon is not a plunge to destruction, but a region of seeming reprieve, the ergosphere we mentioned, where you are forced to spin with the black hole. But if you could press further inward, you would cross a second inner horizon. This is the Cauchy horizon, and it is a boundary of a different, more terrifying kind. It is not a point of no return for matter, but a point of no return for physics itself. Beyond the Cauchy horizon, Einstein's equations tell us that predictability completely breaks down. The future is no longer determined by the past. Cause and effect unravel. It is a realm of pure mathematical chaos where anything could, in principle, happen. The very fabric of space-time becomes so violently twisted that it might allow for paths that loop back on themselves, known as closed time-like curves. This is the science fiction concept of a time loop, written into the cold, hard math of general relativity. Within this infinitely warped core, you could theoretically travel on a path that brings you back to an earlier moment in your own timeline. You could meet your younger self falling in behind you. The equations permit it, but does reality? Most physicists believe these features are mathematical artifacts, hints that our current theory reaches its limits in such extreme environments. The inner horizons might be violently unstable, collapsing into a wall of infinite energy, a singularity, the moment any matter or even radiation tries to cross them. The universe may have a cosmic censorship law, preventing these paradoxical regions from ever being seen. Yet, the mere possibility forces us to confront the strangeness we have unleashed. A rotating black hole is not a simple pit. It is a layered labyrinth of broken physics, containing zones where time becomes a maze and the future is not written. It is a stark reminder that inside the darkness, our most fundamental concepts of sequence and consequence might simply cease to apply. The time loops within a spinning black hole hint at a universe where even the darkest objects are not permanent. This leads to a profound and unsettling question. Can a black hole die? The classical answer from Einstein's theory was a resounding no. A black hole, once formed, was a permanent fixture in the cosmos, a gravitational pit that could only grow larger by consuming more mass. But in the 1970s, Stephen Hawking performed a brilliant calculation that changed everything. He realized that the intense gravity at the event horizon does not exist in a vacuum. It interacts with the quantum foam, the seething sea of virtual particle pairs that constantly flicker in and out of existence everywhere in space. Normally, these pairs annihilate each other almost instantly. But right at the edge of a black hole, a strange theft can occur. One particle of the pair falls into the black hole while its partner escapes into space. To an outside observer, it looks as if the black hole is emitting a faint glow of particles, now called Hawking radiation. There is a cost for this creation. The energy to make the escaping particle comes from the black hole's own mass. So, very slowly, over timescales that dwarf the current age of the universe, the black hole loses mass and energy. It evaporates. For a star-sized black hole, this process is agonizingly slow. taking longer than a 1 followed by 67 zeros years. But for a tiny, hypothetical primordial black hole, it could be happening now. The smaller the black hole, the hotter its Hawking radiation and the faster it evaporates. As it shrinks, it gets hotter and evaporates even faster in a runaway process that suggests a final, explosive end. And here lies the ultimate mystery. What happens in that last instant? Does the black hole simply vanish, popping out of existence and leaving empty space behind? If so, what happens to all the information about everything that ever fell into it? This is the final, fatal confrontation of the information paradox. If the black hole disappears completely, then the information is irretrievably lost, violating quantum law. To avoid this, some theories propose a different ending. Perhaps the evaporation stops at the very last moment, leaving behind a tiny, stable, and incredibly dense remnant, no larger than a grain of sand but containing the entire information content of the original black hole. This remnant would be a fossil, a permanent record of the black hole's history, solving the paradox by locking the information away forever in an object we could never access. Another, more dramatic possibility is that the final evaporation is not silent. As the black hole approaches the size of a single atom, its temperature soars to billions of degrees. The last fraction of a second could be a blinding flash of high-energy radiation, a final shout containing, in some scrambled code, all the information it ever swallowed. We may never live long enough to witness a black hole's death, but understanding its end is the key to unlocking the deepest laws that govern reality, time, and memory itself. The slow death of a black hole is a lonely whisper in the dark, but in the crowded hearts of galaxies, black holes are anything but lonely, and their interactions create some of the most violent and informative events in the cosmos. This brings us to a curious empty space on the cosmic scale, a mysterious boundary line drawn by gravity itself. Astronomers have noticed a strange and persistent gap. On one side, we find neutron stars, the ultra-dense cores left after a giant star explodes. These are city-sized balls of pure neutron matter, so dense that a single teaspoon would weigh as much as a mountain. The most massive neutron stars we have observed weigh just over 2 times the mass of our Sun. On the other side, we have stellar mass black holes, born from the collapse of even more massive stars. The lightest black holes we have confidently detected, thanks largely to gravitational wave observatories, weigh at least 5 solar masses. Between roughly 2 and 5 solar masses, there is a puzzling desert, a mass gap where almost no compact objects have been found. It is as if nature has a rule, a forbidden zone between the ultimate stable star and the ultimate collapse. Why does this gap exist? The physics of stellar death provides a clue. When a massive star runs out of fuel, its core collapses. If the leftover core is below a certain critical mass, the crush is halted by a quantum force called neutron degeneracy pressure, creating a neutron star. But if the core is too heavy, even that incredible pressure fails. Nothing can stop the collapse and a black hole is born. The gap suggests the dividing line is sharp and that there are not many stars whose cores end their lives in that precise in-between weight class. But the universe loves exceptions. Could something strange and exotic be hiding in this gap? One tantalizing possibility is the quark star. A neutron star is made of neutrons, but under even greater pressure, those neutrons themselves might break down into their constituent parts, quarks. This would create a soup of free quarks, a state of matter not seen since the first microsecond after the Big Bang. A quark star would be slightly smaller and denser than a neutron star, and it could theoretically exist in that mass gap, a temporary, unstable state on the very brink of becoming a black hole. Another candidate is a hypermassive neutron star formed when 2 neutron stars collide. For a brief, violent moment, the merged object might be propped up by its incredible rotation, a spinning, wobbling monster weighing in the gap before it finally succumbs to gravity and collapses into a black hole. Or perhaps the gap is an illusion of our limited vision. Maybe there are tiny black holes born from peculiar stellar processes or ancient primordial origins that are just waiting to be found in that silent zone. Every new gravitational wave signal, every flash from a colliding star, is a probe into this mysterious boundary. Finding an object firmly in the mass gap would be a monumental discovery, forcing us to rewrite the final chapters of stellar evolution and revealing new, extreme states of matter that defy our imagination. Gravity may pull matter in, but magnetism decides its final, spectacular fate. While the immense gravity of a black hole creates the stage, it is the invisible, coiled power of magnetic fields that directs the cosmic drama. These fields, often overlooked in the shadow of gravity's raw power, are the architects of the most violent and luminous phenomena in the universe. They do not originate from the black hole itself, which according to classical physics has no magnetic field of its own. Instead, they are born from the chaotic inferno of material swirling around it, the accretion disk. As this superheated plasma of gas and dust spirals inward at nearly the speed of light, charged particles within it generate and amplify magnetic fields, winding them into coils of unimaginable tension. These magnetic fields become so strong they can rival gravity itself, channeling and controlling the flow of matter with a ferocious will. Their most breathtaking achievement is the creation of relativistic jets. These are narrow, focused beams of charged particles that blast outward at over 99% the speed of light, shooting from the black hole's poles for thousands or even millions of light years into intergalactic space. They are cosmic blowtorches powered not by the black hole's gravity, but by the twisted magnetic fields that act like a slingshot, extracting rotational energy from the black hole or its disk and launching material into the void. It is these magnetic jets beaming their intense radiation across the cosmos that power the brilliant quasars we see in the early universe, turning a dark gravitational pit into the brightest beacons in existence. The fields also dictate the very structure of the accretion disk, creating turbulence and friction that heats the material to millions of degrees, causing it to glow in X-rays before it vanishes. Yet, for all we see their effects, a central mystery remains. How are these magnetic fields, which must be billions of times stronger than any magnet on Earth, generated and sustained with such perfect, focused power? The process, known as the dynamo effect, is a chaotic feedback loop we struggle to simulate. It is the hidden conductor of the cosmic orchestra, orchestrating a light show of terrifying beauty from the edge of oblivion. Without magnetism, a feeding black hole would be a silent, dark feast. With it, the universe gets a firework display that echoes across eternity. The magnetic fury around a black hole is a spectacle for outsiders, but the true final act is a private performance witnessed only by the doomed. To cross the event horizon is to step into a theater where the laws of physics become a personal, sensory experience. Let us follow an astronaut on this one-way journey and see the universe through their eyes as they fall toward two very different black holes. First, imagine a stellar mass black hole, perhaps 10 times the mass of our Sun. From a safe distance, it is a perfect circle of darkness against the star field. As our astronaut begins their fatal approach, feet first toward the center, the first thing they notice is the tide. The pull of gravity on their feet is measurably stronger than the pull on their head. This difference, gentle at first, begins to stretch their body. Within minutes, it becomes unbearable, a relentless force pulling them into a long, thin strand, spaghettifying them long before they reach the horizon. The view, however, is utterly bizarre. Looking ahead toward the black hole, they see only darkness, but looking back or to the sides, the entire universe appears warped, as if seen through a giant fisheye lens. The light from distant stars is bent into a bright ring around the black hole's shadow. As they fall, this ring tightens around them. Time for them feels normal. Their watch ticks forward second by second. They cross the event horizon with a sudden, silent transition. feeling nothing special at that mathematical boundary. But from the perspective of a friend watching from a safe ship, the story is one of eternal farewell. As the astronaut falls, their signals back to the ship become more and more redshifted, stretched to longer and longer wavelengths. Their image dims and reddens, slowing down as if caught in cosmic glue. From the outside, they appear to freeze in time, hovering just above the horizon, their final wave never quite reaching the ship. They become a fading fossil, etched onto the surface of the black hole from an external point of view. Now, consider a fall into a supermassive black hole, like the one at the center of our galaxy, weighing millions of suns. Here, the tidal forces are so gentle over such a vast distance that our astronaut could cross the event horizon completely unharmed, at least initially. The spaghettification would not begin until deep inside the black hole's interior. The journey would be calm, even serene. The view would be even more spectacular. The warped sky would show not just the ring of light, but multiple distorted images of the entire galaxy, wrapped around the darkness in concentric circles. They could watch millennia of cosmic history play out in fast-forward as they fall, seeing the light from stars that arrived over eons all compressed into their final minutes. They would cross the horizon quietly, still able to see the universe outside, though it would appear as a bright, shrinking disk of light above them. For them, the passage from the horizon to the final fate at the singularity might take hours. For the outside universe, their image still fades to red and freezes forever at the edge. This is the brutal paradox of relativity. For the falling observer, it is a finite journey ending in a violent or mysterious conclusion. For the universe they left behind, they are a ghost, a story paused mid-sentence for all of time. One reality holds a quick, if strange, death. The other holds an eternal monument. Which one is truly real? The answer depends entirely on where you stand, a final lesson in the profound subjectivity of time and space. The frozen image of an astronaut on the horizon is more than a ghost. It could be a fundamental clue to the nature of reality. This leads us to a truly mind-bending unknown. Are black holes holographic? The idea sounds like science fiction, but it emerges from the deepest trenches of theoretical physics. It is called the holographic principle, and it proposes a staggering rewrite of our universe's blueprint. In our everyday experience, information seems to require 3 dimensions. To describe a statue, you need height, width, and depth. But the holographic principle suggests that all the information needed to describe everything within a certain volume of space, including every particle, every force, every event, can be perfectly encoded on a 2-dimensional surface surrounding that volume. Think of the hologram on a credit card or a driver's license. It is a flat, etched surface, but when light hits it, it projects a 3-dimensional image that seems to float in space. The information for that entire 3D image is stored entirely on the 2D plastic. The holographic principle argues our universe might work the same way. The 3 spatial dimensions we move through could be a grand projection from information stored on a distant 2-dimensional boundary, and black holes provide the ultimate test case. Remember the information paradox, the war between quantum mechanics and general relativity over whether data is lost inside a black hole. The holographic principle offers a breathtaking solution. It suggests that when matter falls into a black hole, its information is not lost in the 3-dimensional interior. Instead, it is immediately and perfectly translated, like a cosmic encryption, onto the 2-dimensional surface of the event horizon. Every atom, every bit of data about the fallen astronaut is stored as a kind of quantum pixel on that spherical membrane. The black hole's interior, the vast volume we imagine, becomes a kind of illusion, a projected reality from the data written on its skin. This is not just a clever metaphor. It comes from the mathematics of string theory, where calculations about black hole entropy, a measure of their information content, mysteriously match calculations based solely on the area of their event horizons. The information capacity of a region of space, it seems, is proportional not to its volume, but to the area of its boundary. So, a black hole, the densest object imaginable, might not be a place at all in the way we think. It could be the universe's most efficient data storage device, a cosmic hard drive where three-dimensional experience is rendered from a two-dimensional code. If this is true for black holes, some physicists take the logic even further. Could our entire observable universe, with all its galaxies and stars, be a holographic projection from information stored on some unimaginably distant spherical surface? The idea redefines what is real. It suggests that the depth we perceive, the space we move through, is a magnificent illusion, a story being read from the surface of something far simpler and stranger. The black hole, then, is not a destroyer of reality, but a window into its true, flat, and profoundly encoded nature. That holographic surface is not a silent record, it has a pulse. From the hearts of feeding black holes across the cosmos, astronomers detect a strange, rhythmic signal, a flickering in the X-ray light that acts like a cosmic heartbeat. These are quasi-periodic oscillations, or QPOS, and they are one of the most tantalizing and frustrating clues we have about the violent dance right at the edge of oblivion. Picture the accretion disk, that whirling maelstrom of superheated gas spiraling toward the event horizon. As we watch it with X-ray telescopes, its light does not shine with a steady glow. It flickers and flares chaotically, but buried within that chaos are distinct, repeating patterns. The light curve, a graph of brightness over time, shows a telltale signature, a series of regular peaks and valleys that rise and fall with a specific frequency, like the steady beat of a drum underlying a chaotic symphony. But quasi means almost, and that is the key. These oscillations are not perfectly regular like a metronome. They drift and change, their frequency shifting slightly over time, as if the drummer is slowly speeding up or slowing down. This imperfect rhythm is what makes them so valuable and so mysterious. They are a direct probe of the most extreme environment in the universe, the final few hundred miles where space is dragged around at nearly the speed of light. But what exactly is causing the beat? The leading theory is that it is a feature of the accretion disk itself. As blobs of hot gas whip around in the inner disk, they might create bright, hot spots that flash like a lighthouse beam every time they swing into our view. The frequency of the flash would tell us the orbital speed at that precise distance from the black hole. Another idea points to a more fundamental process. The inner edge of the accretion disk is not a sharp cutoff. There is a region where stable orbits become impossible, and matter begins its final, fatal plunge toward the horizon. The interface between the last stable orbit and this plunging region could be unstable, causing the entire inner disk to wobble or pulsate in a rhythmic way, like water sloshing in a bucket. This sloshing would modulate the X-ray light, creating the observed oscillations. The most exotic possibility is that we are not seeing matter at all, but the very fabric of space-time ringing like a bell. Just as a struck gong vibrates at specific frequencies, the immense gravity of the black hole could cause space-time around it to oscillate in set patterns. These are the gravitational wave modes of the black hole itself, and if matter in the disk is somehow coupled to these vibrations, it could cause the X-ray light to pulse in sync. Each explanation paints a different picture of the black hole's final frontier. The hotspot model gives us a map of the disk's geography. The sloshing model reveals the dynamics of matter on the brink. The space-time ringing model offers a way to hear the black hole's gravity directly. By studying the precise frequencies and how they change, astronomers are trying to decode this signal. It is as if we are listening to the black hole's heart monitor, trying to diagnose the conditions in a place where our intuition fails. Every flicker is a message from the edge, written in a code we are still struggling to crack. The rhythmic heartbeat of a feeding black hole is a signal from the edge of our reality. But what if that edge is not an ending at all? Our 16th unknown ventures into the most speculative territory yet, asking if black holes are not tombs but wombs. Could these points of infinite collapse be the birthplaces of entirely new universes, hidden within our own? The idea that a black hole might be a gateway to another cosmos is a staple of science fiction, but it finds surprising echoes in the equations of theoretical physics. One of the most provocative visions comes from physicist Lee Smolin and his theory of cosmological natural selection. Smolin proposed a truly cosmic form of evolution. In this view, when a star collapses into a black hole, the singularity at its core does not mark a dead end. Instead, it undergoes a bounce, a rebound that creates a new, expanding universe in a region of space-time completely disconnected from our own. This baby universe would inherit but slightly tweak the fundamental physical constants of its parent. Think of it like cosmic reproduction with random mutations. Some of these newborn universes would, by chance, have constants fine-tuned to produce many black holes. Those prolific universes would then have more offspring, spreading their fruitful physics across the multiverse. Over cosmic time, this selection pressure would favor universes like our own that are excellent at making black holes. It is a breathtaking cycle where every star that dies in a supernova might be sowing the seeds for an infinity of new cosmic landscapes, each with its own unique laws of physics. Another thread connects this idea directly to our own origins. If black holes can give birth to universes, then what about the Big Bang? Some cosmologists have flipped the script entirely, suggesting our entire cosmos is not the first chapter, but a later paragraph in an infinite story. In this scenario, the Big Bang singularity was not a mysterious beginning from nothing, but the white hole eruption from a black hole that formed in a parent universe. Our expanding universe, in all its glory, would be the interior of that other universe's black hole seen from the inside. Picture it not as an explosion in empty space, but as a bubble of new spacetime pinching off from an older, grander cosmos. This creates a surreal, almost fractal image of reality, a multiverse where universes are nested within each other like Russian dolls, each born from the catastrophic death of a star in a universe one level up. The visual is staggering, a silent, dark sphere in our cosmos containing, within its unknowable interior, an entire fledgling universe with its own galaxies, stars, and perhaps even its own black holes budding further universes in an endless chain. While these ideas remain highly speculative, far from proven science, they transform the black hole from a symbol of finality into one of transcendence. It suggests that the darkest, most destructive events in our universe could be the very engines of creation, spinning out new realities where life and light might begin again under different skies. The ultimate cosmic recycling bin might just be a maternity ward for entire worlds. The possibility of new universes begins with a single star's death, a process governed by one of the most precise numbers in all of nature. This is the Chandrasekhar limit, the cosmic rulebook that decides whether a star's corpse becomes a diamond-like white dwarf or collapses into something infinitely darker. For a white dwarf, a stellar ember supported by the quantum pressure of its electrons, this limit is about 1.4 times the mass of our Sun. It is a line drawn in the sand by the laws of physics. If a white dwarf stays below this mass, it cools forever in peace. But if it gains even a sliver more mass, perhaps by siphoning gas from a companion star, it crosses the threshold. At that moment, electron pressure shatters, gravity wins utterly, and the star embarks on a catastrophic collapse that will forge a neutron star or a black hole. This precise number is why we have the cosmic landscape we do, a universe dotted with both glittering dwarf remnants and gravitational abysses. Yet what happens in the heartbeat after that limit is crossed is one of the most violent and poorly understood events in the cosmos. The core of a massive star, having fused its way to iron, suddenly finds itself without a source of energy to fight gravity. it collapses inward at a quarter the speed of light. In less than a second, a city-sized core is crushed into a sphere just a dozen miles across. The density becomes so insane that protons and electrons are forced together, merging into neutrons and releasing a flood of ghostly particles called neutrinos. These neutrinos carry away 99% of the dying star's energy in a torrent that outshines the entire galaxy. For a brief moment, the collapse might halt. The newborn neutron star is so dense that neutron pressure, a force even stronger than electron pressure, might stop the fall. This sudden stop creates a shock wave, a seismic bounce that races back outward through the infalling layers of the star. If this shock wave is powerful enough, it will blow the star apart in a spectacular supernova, scattering the elements of life across space and leaving the neutron star behind. But sometimes the bounce fails, the shock wave stalls, losing energy as it plows through the immense overlying material. It falters and begins to fall back inward. In this scenario, there is no second chance. The newborn neutron star, already under unimaginable pressure, is crushed further by the returning weight of the star's own outer layers. If its mass exceeds about 2 or 3 times that of our Sun, even neutron pressure gives way. Nothing in the known universe can halt the descent. The collapse continues past the point of a neutron star, past any conceivable structure, and the event horizon forms. A black hole is born in silence, deep within the shrouded heart of a failed explosion. We see the brilliant supernova that succeed. The ones that fail to explode, that silently become black holes, are far harder to catch in the act. They are the ghosts of the Chandrasekhar limit, stars that crossed the line and found no way back, vanishing from our visible universe to leave only gravity behind. This moment of decision, this turbulent battle between outward shock and inward pull, is where the elements of our world are forged and where the darkest objects are seeded. We are only beginning to simulate the chaotic physics of that single, universe-altering second. That silent birth leaves behind a ghost drifting through the galactic night. Our 18th unknown confronts a sobering fact. We have never directly seen an isolated, stellar mass black hole. Every one we know about is announced by the company it keeps. We find them in binary systems where their immense gravity violently strips gas from a companion star, creating a telltale X-ray glow. We have heard them in the ripples of space-time as pairs of black holes spiral together and merge in a final gravitational wave shout. But what of the loners? Theory tells us the vast majority of black holes, perhaps the lonely remnants of stars that died alone, should be drifting in perfect silence through the Milky Way. They are the ultimate dark wanderers, invisible against the black of space, their presence betrayed only by the subtlest of fingerprints on the fabric of reality itself. Finding one is the ultimate cosmic detective story, and it requires looking not for light but for the bending of light. The method is called astrometric microlensing. You are familiar with the concept of a lens. If a massive object like a black hole passes almost directly between us and a distant background star, its gravity will act as a natural lens. It will bend and magnify the star's light, causing a temporary brightening that can last days or weeks. But for a single, invisible black hole, there is an even more precise signature. As the black hole moves, its gravitational field doesn't just magnify the background star, it slightly shifts the star's apparent position in the sky. It is an incredibly tiny shift, a wobble measured in micro-arcseconds, less than the width of a human hair seen from a mile away, but our telescopes are becoming precise enough to catch it. Imagine a single pinpoint star in a distant galaxy. For years, it sits fixed in its place. Then, for a period of months, its position begins to trace a tiny, perfect loop in the sky, as if pushed by an unseen hand before settling back to its original spot. That loop is the signature of a dark, compact mass drifting through the foreground, its gravity warping our line of sight. No brightening, no X-rays, just the silent geometry of bent starlight. The beauty of this method is that it does not rely on the black hole doing anything at all. It simply has to exist and move. A successful detection would give us more than just a trophy. It would tell us the black hole's mass with remarkable precision and confirm its solitary nature. It would allow us to take a census of these dark ghosts to understand how many are truly out there, drifting unseen through the spiral arms. It would be a direct glimpse into the silent majority of stellar corpses, the dark foundation of our galaxy's history. Until we catch one in the act, these lone black holes remain theoretical phantoms. They are the unseen anchors in the dark, their presence felt only in the quietest distortion of a star's true place in the heavens. A silent, drifting black hole is a perfect thermodynamic system. It hides a secret identity, one that connects the coldest voids in space to the very science of heat and disorder. This is the profound link between black holes and thermodynamics, a relationship so deep it rewrites our understanding of both gravity and information. The journey begins with a single, startling equation carved onto the tombstone of a physicist named Jacob Bekenstein. In the early 1970s, Bekenstein made a radical proposal: black holes have entropy. Entropy in thermodynamics is a measure of disorder or randomness in a system. It is why ice melts in a warm room and why your desk never spontaneously tidies itself. The second law states that the total entropy of the universe always increases. Bekenstein argued that when you throw a hot, high-entropy object like a cup of coffee into a black hole, you are hiding that disorder from the universe. To preserve the second law, the black hole itself must gain entropy, becoming a repository for cosmic messiness. His calculation was breathtakingly simple. A black hole's entropy is proportional to the area of its event horizon, not its volume but its surface area. This was the first hint of the holographic principle, the idea that information about a three-dimensional volume is stored on its two-dimensional boundary. Then Stephen Hawking entered the conversation and things got even stranger. Hawking showed that if a black hole has entropy, it must also have a temperature. Anything with a temperature emits radiation. His famous calculation proved that black holes are not perfectly black. They glow with a faint heat, now called Hawking radiation. This temperature is inversely related to the black hole's mass. A giant, supermassive black hole has a temperature barely above absolute zero, a whisper of heat. A tiny black hole would be searingly hot, evaporating in a flash. This completed the analogy, forging the laws of black hole mechanics that perfectly mirror the classical laws of thermodynamics. The first law, conservation of energy, becomes a statement about the mass, spin, and energy of a black hole. The second law, the increase of entropy, becomes the statement that the total area of all black hole horizons in the universe can never decrease. This is not a vague similarity. It is a mathematical equivalence suggesting that gravity, at its most extreme, is fundamentally a thermodynamic phenomenon. But this raises a haunting question. In an ordinary gas, entropy arises from the countless microscopic configurations of its molecules, the different ways atoms can be arranged while still looking like the same gas from the outside. So, if a black hole's entropy is proportional to the area of its horizon, what are its microscopic parts? What are the atoms of space-time whose different arrangements give rise to this immense disorder? This is the central mystery. We have the equation, but we lack the picture. String theory suggests these fundamental bits could be tiny, vibrating strings attached to the horizon. Loop quantum gravity proposes they are quantized, pixel-like units of area, each carrying a tiny bit of information. Each possibility paints a different portrait of the vacuum itself, suggesting that empty space is not empty at all, but a vast, structured network of information at the Planck scale. The event horizon is a ledger, and its entropy is the count of every possible way that ledger could be written while still describing the same black hole to an outside observer. Finding those fundamental entries, those quantum degrees of freedom, would be to read the fine print of reality, to see the pixels from which the universe is rendered. The black hole, therefore, is not just an object in space. It is a thermodynamic engine, a cosmic archive, and our most powerful clue that space-time itself is built from something deeper, something that can be hot, disordered, and profoundly encoded. Beyond the last stable orbit, the laws of physics shift into a final, irreversible gear. This is the plunging region, a newly emphasized zone of space-time that is not quite the event horizon, but is just as final. For decades, our models of black holes focused on two main areas, the stable accretion disk and the point of no return itself. But recent theoretical work has sharpened our view, revealing this critical boundary layer where matter makes its last fateful dive. Imagine the accretion disk as a river spiraling toward a waterfall. The plunging region is the point where the river's current finally overpowers everything, where the water tips over the edge. Here, just outside the event horizon, the pull of gravity becomes so overwhelming that even light-speed orbits are impossible. Matter is not spiraling anymore, it is in free fall, accelerating to nearly the speed of light as it plummets toward the darkness. This is not a place of stable structure, but of chaotic terminal descent, and the new, thrilling possibility is that this region might not be completely dark. As the doomed matter is stretched and heated to incredible temperatures in its final moments, it could emit a last, desperate flash of light, a specific signature of X-rays or other radiation that carries the imprint of the black hole's most extreme gravity. For the first time, we might be able to see the waterfall itself, not just the river flowing toward it. This changes everything for testing Einstein's theory. The plunging region is where the predictions of general relativity are pushed to their absolute limit, where space-time is not just curved, but is cascading inward like a cosmic avalanche. By analyzing the light from this zone, if we can detect it, we could look for subtle deviations from Einstein's equations, hints of new physics or quantum gravity effects that only manifest in such an extreme environment. It is a direct probe of gravity in its strongest possible regime. The Event Horizon Telescope gave us the shadow, the silhouette of a black hole. Observing the plunging region would be like seeing the fiery outline of the waterfall's edge, the moment where matter surrenders completely to the darkness. It would transform the black hole from a static icon into a dynamic process we can watch in real time, revealing the final chapter in the story of everything that falls in. The thermodynamics of a black hole's horizon points to a hidden quantum structure, a network of information that might weave the fabric of space itself. This leads us to one of the most elegant and radical ideas in modern physics, a proposal that two of Einstein's greatest puzzles are actually the same thing. It is called the ER equals EPR conjecture, and it suggests that wormholes and quantum entanglement are two faces of a single, deeper reality. The name itself is a clue. ER stands for Einstein and Rosen, who in 1935 first described the theoretical tunnel through spacetime we call a wormhole, or an Einstein-Rosen bridge. That same year, Einstein, along with Podolsky and Rosen, published a famous paper highlighting the bizarre, spooky action at a distance of quantum entanglement, where two particles become linked so that measuring one instantly affects the other, no matter how far apart they are. For decades, these were seen as separate oddities, one from relativity, the other from quantum mechanics. But what if the eerie connection of entanglement is not spooky action, but a microscopic thread of spacetime itself? The conjecture proposes exactly that. Imagine two entangled particles like a pair of dice that always land on matching numbers even when rolled in different galaxies. According to ER equals EPR, that mysterious quantum link is physically described by a tiny, non-traversable wormhole connecting them. The particles are not communicating faster than light. They are, in a geometric sense, already touching through a shortcut in the fabric of reality. Now scale this idea up to a cosmic level. Take two black holes. If you could somehow entangle them, perhaps by creating them from the same quantum event or by carefully manipulating matter around them, the conjecture suggests a breathtaking consequence. A full-fledged geometric wormhole, an Einstein-Rosen bridge, would form between them, stitching their interiors together. The entangled black holes would be connected by a tunnel through space-time, a bridge built not from matter but from quantum information. This provides a stunning potential solution to the information paradox. Information that falls into one black hole would not be trapped forever at its singularity. Instead, it could travel through the quantum bridge, the wormhole, and emerge from the other black hole, encoded in the Hawking radiation it emits. The information is not lost, it simply takes a hidden shortcut to escape. It is as if you burned a letter here, and its ashes miraculously reassembled inside a locked vault on the other side of the world, because the two locations were secretly connected by a passage we could not see. This vision transforms our picture of the cosmos. Space itself, the void that separates stars and galaxies, may not be fundamental. It could emerge from a vast cosmic web of quantum entanglement, with every connected particle or object linked by unimaginably complex threads of spacetime geometry. Black holes, then, are not just endpoints. They could be portals in this network, knots where the quantum fabric of connection is pulled tight into a visible gravitational knot. The universe becomes less a collection of separate objects in empty space, and more a single, deeply interconnected entity, where every quantum link is a stitch in the tapestry of reality. The distance between 2 points may be an illusion, a story told by the depth of the quantum entanglement between them. That quantum bridge is forged in a crucible of motion, a spin so violent it threatens to tear the fabric of reality apart. Every black hole we know of is spinning, a legacy of the star that birthed it, but this rotation is not infinite. Physics imposes a cosmic speed limit, a point where the black hole becomes extremal. At this maximum spin, the event horizon spins at the speed of light itself. Visualize it not as a sphere, but as a disk flattened by centrifugal force into a razor-thin edge. The ergosphere, that region of dragged spacetime, swells to touch the horizon. The inner structure we discussed, with its chaotic inner horizons and potential for time loops, collapses into a single, infinitely thin ring. This is the edge of mathematical possibility for a classical black hole. But what does the universe do at this limit? The equations of general relativity suggest something strange and perhaps unstable. As the black hole approaches this extremal spin, the forces at its core become unimaginably tense. Some calculations hint that adding even a single grain of dust could push it over the limit, violating cosmic censorship and exposing a naked singularity to the universe, a point of infinite gravity with no event horizon to hide it. This is thought to be forbidden by the laws of physics, as it would make causality and predictability break down on a cosmic scale. So, does spacetime rebel? Does some new, repulsive quantum force emerge to prevent this violation, a force we have not yet discovered? The extremal limit could be a gateway, a place where the smooth predictions of Einstein's theory fray, revealing the stitches of quantum gravity underneath. It is a laboratory we cannot visit, but we can observe its effects from a safe distance. We measure a black hole's spin by studying the X-ray light from its accretion disk. As matter whirls in that final, hot orbit, the light it emits is distorted by the intense gravitational and Doppler effects caused by the black hole's drag. By untangling the precise shape of the X-ray spectrum, astronomers can calculate just how fast the monster is turning. So far, every measurement shows black holes spinning rapidly, some at over 90% of the maximum possible rate, but none have ever been found at the theoretical limit itself. This absence is a clue. It suggests nature has a safety mechanism, a law that prevents spacetime from being wound too tight. Perhaps at the brink, the black hole becomes a perfect mirror, or perhaps it sheds energy through gravitational waves to keep itself in check. The search for a black hole spinning at the absolute edge is a search for a crack in our understanding, a place where the universe's deepest rules are written in the blur of a horizon moving at light speed. A cosmic rain of unimaginable power constantly bombards our planet, and we have no idea where it comes from. These are ultra-high-energy cosmic rays, single atomic nuclei hurtling through the void with the force of a major league fastball, condensed into a single subatomic particle. They carry millions of times more energy than anything our most powerful particle colliders on Earth can produce. For over a century, their origin has been one of the greatest puzzles in astrophysics. What natural engine in the cosmos could possibly accelerate a particle to such insane speeds? The prime suspect, hiding in plain sight, is the universe's most powerful dynamo, the supermassive black hole. Not the black hole itself, but the colossal machinery that surrounds it. Picture the relativistic jets we discussed earlier, those narrow beams of plasma shooting from the black hole's poles at nearly light speed. Within these jets, spanning thousands of light years, exists a chaotic maelstrom of magnetic fields. These fields are not calm and orderly. They snap and break, violently rearranging themselves in a process called magnetic reconnection. Think of it as a cosmic short circuit on an unimaginable scale. When magnetic field lines of opposite direction are forced together, they can suddenly break and reconnect in a new configuration. This explosive event releases a colossal amount of stored magnetic energy, flinging charged particles trapped within the jet to velocities approaching the speed of light. It is a natural particle accelerator of stupendous power, a slingshot woven from twisted spacetime and magnetic fury. A supermassive black hole like the one in the galaxy M87, with its famous jet stretching for 5,000 light-years, is a perfect candidate. Its jet is a continuous, high-voltage cable stretching across intergalactic space, and anywhere along its length, magnetic reconnection could fire a proton or an atomic nucleus across the cosmos like a bullet from a railgun. Even our own galactic center, Sagittarius, a star, though relatively quiet now, may have had violent outbursts in the past that could have produced such particles. The challenge is tracing these cosmic bullets back to their source. Unlike light, cosmic rays are charged, so their paths are bent and scrambled by the magnetic fields that fill the galaxy. By the time one strikes our atmosphere, creating a shower of secondary particles, it is impossible to point directly back to its origin. We are detectives at the scene of a crime, studying the bullet but with no clear line back to the gun. Yet, by combining observations of black hole jets with the detection of these ultra-energy particles, we are slowly building a case. Each cosmic ray that slams into our sky is a messenger from the most violent neighborhoods in the universe, carrying a coded story of magnetic fields snapping like rubber bands and particles surfing waves of pure energy at the edge of a black hole's wrath. That cosmic bullet's journey is measured by clocks that tick at wildly different rates. Time itself becomes a fluid, personal experience in the grip of a black hole's gravity. We have touched on this strange slowing, but its ultimate consequence is a reality so twisted it challenges the very nature of observation. From the safety of a distant spacecraft, you watch a probe make its final approach toward the event horizon. As it gets closer, a bizarre transformation occurs. The light from its hull begins to stretch, shifting from visible colors down to red, then to infrared, and finally to imperceptible radio waves. Its signals slow to a crawl, each beep arriving with a longer and longer delay. The probe itself seems to decelerate, approaching the horizon with infinite slowness. From your perspective, it never actually crosses. It fades to black and red, its final image freezing like a fossil on the threshold of the darkness, a permanent monument to its last moment. This is not an illusion of slow light. It is the direct effect of extreme gravitational time dilation. Time for the probe from your distant viewpoint has effectively stopped. A second for the probe becomes an eternity for you. This leads to a profound and strange implication for the black hole's own history. If nothing ever appears to cross the horizon from the outside, then how does the black hole ever grow? The resolution lies in the quantum nature of reality. The frozen image is not a solid shell. It is a photosphere, a layer of infinitely redshifted light from all the matter that has ever fallen in. From afar, the black hole appears shrouded in this ghostly, timeless film. But in the frame of the falling matter itself, time passes normally. It crosses the horizon in a finite, often quick, interval and adds its mass to the black hole from the inside. The universe outside updates the black hole's gravitational field at the speed of light, so the hole grows and its horizon expands, even as the last visual evidence of its meal remains eternally stuck at the edge. Now consider the trippy fate of that frozen image. As more matter falls in, new frozen images stack up, layered over the old ones. In principle, the entire history of the black hole's accretion could be encoded on this photosphere, like frames of a movie permanently etched onto the surface. If you could somehow see without the redshift, you might witness the entire infall process playing out in slow motion, all at once on that spherical screen. This extreme dilation also stretches any radiation from the black hole's surroundings to incredible degrees. A single flash of light emitted just outside the horizon could be stretched from our point of view to last for the entire future lifetime of the universe. The final moments of a black hole's evaporation, happening in a blink from its own perspective, might be drawn out into an achingly slow fade over eons for any distant survivors. It creates a cosmic paradox of perspective, where an event that is quick and violent in one frame of reference is a near-eternal, frozen tableau in another. There is no universal now. The black hole teaches us that time is not a river flowing at the same rate for everyone. It is a personal, malleable experience, and at the event horizon, it fractures completely, leaving one reality forever outside and another forever within. This cosmic speed limit hints at a black hole's final, stable form, but the universe is filled with forms we have yet to find. We have mapped the stellar corpses and the galactic giants, but between them lies a ghostly desert, a missing link in the black hole family tree. These are the intermediate mass black holes, the cosmic middleweights, with masses ranging from a few hundred to a few 100,000 times that of our Sun. They should be the crucial stepping stones, the missing rungs on the ladder that explain how supermassive black holes grew from stellar seeds. Yet for decades, they have been almost impossible to find, hiding in plain sight. Why is their discovery so vital? Think of it as tracing the life of a giant. To understand how a creature grows to be 100 feet tall, you need to find its adolescent bones. If supermassive black holes really did start as star-sized seeds, they must have gone through a middle phase, a period of rapid growth by feasting on gas and merging with others. These intermediate black holes would be the fossils of that violent adolescence. Without them, the growth story has a gaping hole. We are left with a giant that appears fully formed in the cosmic crib with no clear history of how it got there. So where are they hiding? The prime hunting grounds are places dense with ancient stars, environments where black holes could easily find partners to merge with or gas to consume. Globular clusters, those shimmering, spherical swarms of hundreds of thousands of stars, are perfect candidates. In these crowded stellar cities, a black hole could sink to the center through gravitational interactions, a dark king at the heart of a glittering kingdom. There, it could merge with other black holes, growing steadily into the intermediate mass range. Astronomers have peered into the cores of several clusters, looking for the telltale, rapid motion of stars whipped around by an unseen, massive anchor. A few tantalizing signals have emerged, like in the cluster Omega Centauri, where stars are orbiting something invisible weighing tens of thousands of solar masses. It is not yet definitive proof, but it is a powerful whisper. Another promising nursery is the humble dwarf galaxy. These are small, faint galaxies, often orbiting larger ones like our Milky Way. They are cosmic relics, relatively undisturbed since the early universe. If a direct collapse black hole seed formed in the dawn of time, it might have ended up in one of these quiet backwaters, growing slowly over eons into an intermediate mass black hole, forever isolated from the chaotic feasts of a galactic core. Finding one here would be like discovering a rare, ancient fish in a secluded mountain lake, a living fossil of black hole evolution. The hunt is painstaking, requiring us to measure the subtle dance of individual stars or the faint X-ray glow from a trickle of accreted gas. Every candidate is precious, a potential key to unlocking the middle chapter of the most powerful objects in the cosmos. Their elusive nature forces us to ask, are they truly rare, or are we just looking with the wrong eyes? Their discovery would do more than fill a gap in a catalogue. It would connect the dots in the life story of cosmic giants, revealing how the darkest seeds in the universe grow to rule the light of galaxies. The horizon's perfect smoothness is a beautiful lie told by classical physics. For decades, we have accepted Einstein's vision of the event horizon as a geometric boundary, a one-way membrane in space-time where nothing special happens locally as you cross. It is an elegant, empty surface, but the brutal demands of quantum mechanics may shatter this serene picture, forcing us to ask if the horizon is truly stable or if it conceals a layer of unimaginable violence. The smooth horizon of general relativity cannot coexist peacefully with the quantum principle that information must never be lost. Something has to give, and the leading candidates are anything but calm. One radical proposal is the firewall. Imagine approaching what you think is the event horizon. Instead of slipping quietly into darkness, you are incinerated. A searing wall of high-energy particles, a literal firewall born from the conflict between the falling particles' information and the Hawking radiation trying to carry it away, vaporizes anything that comes near. This firewall would reside just outside the classical horizon, a blistering shield that destroys information by preventing it from ever entering the black hole in the first place. It preserves quantum mechanics by being brutally unforgiving, but it utterly violates the gentle passage promised by Einstein's theory. The horizon, in this view, is not a place you cross. It is a place where you end. An even more profound reimagining comes from string theory with the concept of the fuzzball. Here, there is no empty interior and no smooth horizon at all. The entire black hole, from what would have been its horizon inward, is replaced by a giant, tangled ball of cosmic strings, the fundamental threads of reality. This fuzzball has a definite, fuzzy surface, but it is not a place of infinite density. It is a physical object buzzing with quantum vibrations, and it contains all the information about everything that ever formed the black hole, stored in its complex, stringy structure. The event horizon is replaced by this turbulent, energetic boundary. There is no inside in the traditional sense, no singularity, just a massive, exotic star made of something far stranger than matter. Crossing it would mean merging with this vibrating quantum mess. These ideas force us to confront the stability of the horizon itself. Is it a permanent, stable feature of space-time, or a temporary, emergent phenomenon that masks a deeper truth? Perhaps the smooth horizon is an illusion that only appears from afar, like the calm surface of a lake that hides a turbulent world underneath. Up close at the Planck scale, the horizon might be a roiling, chaotic foam of quantum fluctuations, a place where space-time itself is constantly being torn apart and rewoven. The very concept of a precise location for the event horizon could be quantum mechanically fuzzy, smeared over a small region. This would mean there is no sharp point of no return, but rather a gradient of increasing quantum fury. Observational tests for these ideas are incredibly challenging, but not impossible. The shadow of a black hole captured by the Event Horizon Telescope has a certain size and sharpness. A turbulent fuzzball surface or a raging firewall might produce a slightly different silhouette, perhaps a blurrier edge or unexpected patterns in the surrounding light. As our telescopes improve, we might one day see hints of this microstructure, evidence that the dark circle in the sky is not an empty void, but the surface of something tangible and tumultuous. The question of the horizon's stability is ultimately a question about the marriage of gravity and quantum mechanics. Is spacetime so robust that it can maintain a perfect, serene boundary even at the edge of oblivion? Or does quantum chaos inevitably erupt, turning the gateway to a black hole into the most violent front door in the universe? The smooth horizon is a placeholder for our ignorance, and behind it may lie a reality far more textured and fierce than we ever imagined. The relentless growth of a black hole's horizon is a silent clock ticking in one direction only. This irreversible expansion connects to one of the deepest enigmas in all of physics, the arrow of time. We experience time as a one-way street. We remember yesterday but not tomorrow. A shattered glass does not reassemble itself. This forward march from order to disorder is governed by the increase of entropy, and black holes, with their entropy tied directly to the area of their event horizons, are the ultimate entropy engines in the cosmos. When anything falls into a black hole, the total entropy of the universe increases dramatically. The horizon area grows, and that growth can never be reversed, not in any finite time. This provides a powerful gravitational anchor for time's arrow on the largest scales. Imagine the entire history of the universe from the Big Bang to the distant future. In the beginning, entropy was incredibly low, a state of exquisite order. As the cosmos expanded and evolved, stars formed and died, and matter clumped into galaxies, entropy increased. And the formation and growth of black holes represent some of the most significant leaps in cosmic disorder. They are entropy sinks, swallowing ordered systems and converting them into a form of information so scrambled that it maximizes randomness. The universe's journey from a low entropy past to a high entropy future is paved with the births and meals of black holes. Their irreversible nature might be the reason the cosmological arrow of time points so decisively forward. Could it be that we remember the past and not the future simply because the past had fewer black holes? That our subjective experience of time's flow is a direct consequence of the universe's relentless drive toward higher entropy, a drive epitomized by these dark, growing spheres. This is more than philosophy. If the link is fundamental, then studying the evolution of black holes across cosmic history is literally reading the story of time itself. The fading glow of the last stars, the slow evaporation of the final black holes in a cold, dark universe trillions of years from now, that is the end point of time's arrow. The black hole is not just an object in time, it is a sculptor of time's very direction, carving the irreversible path from what was to what will be. Time's arrow points toward a cold, empty future, a fate seemingly written by dark energy. This mysterious force, causing the expansion of the universe to accelerate, is the dominant power in the cosmos today. But what is its relationship with the universe's ultimate gravitational pits? Our 28th unknown asks a profound question. Does dark energy affect black holes, or do black holes simply ignore it? It is a cosmic tug of war between the force that pushes everything apart and the objects that pull everything in. On the largest scales, dark energy is winning, stretching the fabric of space itself and driving galaxies apart. Yet, on the local scale of a solar system or a galaxy, gravity holds firm. A black hole's immense pull keeps its immediate surroundings, its event horizon and accretion disk tightly bound, unaffected by the universe's overall expansion. You and I are not being pulled apart by dark energy because the gravity of the Earth, the Sun, and the Milky Way overpowers it locally. For a black hole, that local grip is infinitely stronger. So, in the present era, a black hole and dark energy exist in separate realms, one ruling the small, the other governing the vast. but the future is a different story. In most models, dark energy is constant, a property of space itself. As the universe expands, more space appears, meaning the total amount of dark energy increases. Its repulsive push grows stronger over cosmic time. Billions of years from now, as galaxies are pulled so far apart that their stars are isolated in a vast, dark void, even the gravitational bonds within a galaxy will be tested. Eventually, the accelerating expansion could overcome the gravity holding individual star systems together. Planets would be torn from their stars. Later, stars would be ripped from galaxies. This leads to the most extreme hypothesis, the Big Rip. In this scenario, dark energy does not just accelerate, it grows infinitely stronger. The repulsive force would eventually surpass every binding force in nature. First, galaxies are shredded, then solar systems, then stars and planets themselves are pulled apart. Finally, in the last moments, even atoms and atomic nuclei would be torn to pieces. Where does a black hole stand in this apocalyptic finale? The event horizon is not a physical object but a boundary in space-time. If dark energy can stretch space-time itself, could it stretch the horizon? Could it eventually overcome the black hole's gravity, causing the horizon to swell, weaken, and finally dissolve? The mathematics is fiendishly complex, but some theories suggest that in a big rip, even black holes would not be safe. As the repulsive force grows to infinity, it could theoretically rip space-time at the singularity itself, effectively evaporating the black hole in a catastrophic, universe-ending instant. The black hole, the ultimate symbol of gravitational dominance, would be undone by the vacuum's repulsion. This is the ultimate cosmic conflict, a battle that will play out over timescales we cannot comprehend. For now, black holes are fortresses, their gravity creating islands of stability in an accelerating sea. But dark energy is the sea itself, and it is rising. Whether it will one day wash over the fortress walls, or whether the black holes will remain as the last dark monuments in a completely dissociated cosmos, is a mystery written in the geometry of a future we will never see. It is the final question of endurance, whether anything, even a singularity, can survive the end of everything. The silent end of all things might be preceded by a cosmic song. We have seen their shadows and felt their tides, but only recently have we learned to listen to them. Black holes, in their most violent acts, create ripples in the fabric of spacetime itself, gravitational waves. These are not sounds in the traditional sense, for space is a vacuum with no air to carry a wave. But if we could hear the vibrations of spacetime, the collision of two black holes would be a crescendo unlike any other. The signal begins as a low hum, a frequency too deep for human ears, as the black holes spiral toward each other over millions of years. As they draw closer, the pitch rises rapidly. The waves grow stronger, shaking the very structure of the universe. In the final milliseconds before they merge, the pitch skyrockets into a distinctive chirp, a cosmic bird call announcing a cataclysm. Then silence. A new, heavier black hole is born from the collision, ringing like a struck bell before settling into quietude. Scientists have translated these gravitational wave signals into sound waves we can hear, and that chirp is now one of the most profound sounds in science, the direct audio signature of reality warping itself. But that iconic chirp is just the first note in a new symphony. With more sensitive detectors coming online, we will tune into a richer orchestra of black hole sounds. Imagine listening to the continuous, low hum of a spinning black hole as it drags spacetime around with it, a perpetual drone underlying the cosmos, or the precise ringdown of a newborn black hole, its quasi-normal mode. This is the sound of the event horizon itself vibrating, wobbling like a drop of water before becoming perfectly smooth. Each black hole has its own unique set of frequencies, determined solely by its mass and spin, a gravitational fingerprint we can hear. By decoding these tones, we can measure the properties of the black hole with incredible precision. testing whether it truly is the simple object described by the no-hair theorem, or if its ring down hides subtle imperfections telling a more complex story. Future observatories in space will listen for frequencies too low for ground-based detectors, the bass notes of the universe. We might hear the steady thrum of millions of pairs of supermassive black holes, all orbiting each other in distant galactic cores, creating a background hum of gravitational waves that fills the cosmos. This would be the soundtrack of galactic evolution, a chorus playing since the universe was young. We are no longer just astronomers looking at the sky. We have become listeners, our instruments tuned to the vibrations of spacetime itself. Every chirp and hum is a direct message from the darkness, a conversation in the language of pure gravity, telling us stories of collision, birth, and the hidden music of the void. That cosmic symphony of gravitational waves may be the internal vibration of a much larger structure. This brings us to the final, most dizzying unknown of all, a question that turns the cosmos inside out. Are we, right now, living inside a black hole? It sounds like the plot of a science fiction novel, but it emerges from a serious, if speculative, attempt to solve the deepest puzzles of our own existence. The idea begins by noticing a strange and profound similarity. Look at the equations describing the birth of our universe, the Big Bang singularity. Now look at the equations describing the singularity at the heart of a black hole. Mathematically, they are eerily similar. Both are points of infinite density where our current laws of physics break down. One is an explosion from a point, the other is an implosion to a point. Could they be two perspectives on the same event? In this radical cosmological model, the Big Bang was not a unique creation from nothing. It was the white hole eruption from a black hole that formed in a larger parent universe. Our entire expanding cosmos, with all its hundreds of billions of galaxies, would then exist inside the event horizon of that external black hole. We are not looking out at the universe from the outside. We are looking out from within a cosmic womb. The evidence is circumstantial but intriguing. Consider the geometry of our universe, measurements of the cosmic microwave background, the afterglow of the Big Bang, suggest that on the largest scales, the universe is remarkably flat and uniform. This is exactly what some models predict for the interior of a sufficiently large black hole, a vast, smooth, expanding space. Furthermore, the total mass of our observable universe, when you calculate it, yields a Schwarzschild radius, the size a black hole of that mass would have, that is astonishingly close to the actual estimated size of the observable universe. It is as if we are living precisely within the volume defined by our own cosmic event horizon. The mind struggles to visualize this, picture our universe not as an island in an infinite void, but as a bubble of space-time. The edge of our observable universe, the limit of how far light has traveled since the beginning, is not a physical wall, but in this model it corresponds to the event horizon of the parent black hole. We cannot see beyond it because that boundary is a one-way membrane from the perspective of the larger universe. Light from outside cannot get into us, just as light from inside a black hole cannot get out. Our entire history, from the hot, dense beginning to the current galactic tapestry, is the story of matter and energy evolving within this immense hidden interior. The cosmic microwave background radiation, that faint whisper of heat from the early cosmos, could be the thermalized glow of the primordial singularity, stretched and cooled over 14 billion years. Every star we see, every planet we walk on, exists in this nested reality. If this is true, it creates a breathtaking, fractal vision of existence. Every black hole that forms in our universe could, in its own unimaginable interior, contain an entire fledgling universe, bubbling into existence with its own laws of physics, its own stars and galaxies. And that universe, in turn, would contain black holes, each birthing another cosmos, in an endless chain of creation within destruction. Our universe becomes one page in an infinite book, a single leaf on an eternal tree. This idea remains highly speculative, far from mainstream consensus, yet it forces a profound shift in perspective. The black hole transforms from a terrifying abyss at the edge of our maps into a potential archetype of creation itself. The darkness we fear might be the very substance of our home. It suggests that to understand the origin of everything, we might not need to look back to a beginning, but inward to the heart of a darkness that has been with us all along. From the possibility that our universe is a cosmic matryoshka doll to the faint hum of gravitational waves, these 30 unknowns are not just gaps in a textbook. They are the bleeding edge of human curiosity, the places where our knowledge dissolves into awe. Each mystery peels back a layer of the black hole, revealing not a simple monster, but the universe's most demanding teacher. We began by shattering the image of a cosmic vacuum cleaner and ended by questioning if we are living inside one. Along the way, we confronted information that might be preserved on a quantum horizon, matter that could be stretched into cosmic strings, and singularities that might birth entirely new realities. These are not random puzzles, they are interconnected clues in a grand investigation, pointing toward a deeper theory that will one day unite gravity with the quantum world. Black holes are the ultimate laboratories, conducting experiments in gravity, thermodynamics, and information science on a scale we could never replicate. They force us to invent new mathematics, to question the nature of time and space, and to accept that reality is far stranger than our intuition allows. The darkness is not empty, it is filled with questions, so as you look up at the night sky, remember that the quiet darkness between the stars holds the most profound riddles of all. Which of these unknowns left you the most astonished or curious? Let the conversation continue down in the comments below. If you enjoyed this journey to the edge of physics, be sure to subscribe for more deep dives into the mysteries of space. Keep looking up, keep wondering, and never stop asking what lies hidden in the dark.